Howdy. Let's talk weather, because it's always safe to talk about weather. So, since a while, I'm claiming that our clouds are plasma. That is a very big thing to say because it would diminish the notion that weather is based on chaos 100%. In other words, it would require a whole new meteorology, and also the forecast possibilities could increase amazingly if weather would be finally understood. So I've been trying to write about clay, and I really managed to get a few sentences done. And yeah, then I just tried to look something up and stumbled again into some trapdoor down somewhere deep in the rabbit hole. That prevented me from writing more about the topic because it was very intriguing. These are just a few pictures. This is several years old, maybe 5 or something, I don't know. And this has been very far away, so already the original, the one on the left, is heavily zoomed in, and obviously the one on the right is increased in order for you to see a little bit more. And obviously it's twisting. And that's also a reason for why I really like to have a good camera, because you never know when you see something like this. And that's just a basic picture. What is it? When you put two pictures in one, just for you to see, to understand better when someone says studying geology is studying petrified weather, because you get the same patterns over and over again. I've been showing this many times. That's just one I just stumbled across. And some time ago, something like this went down in Switzerland. That is also very intriguing. I don't know if that yellow cloud, this one, is emerging from the mountain or from behind the mountain. I wouldn't be surprised at all if it would emerge from the mountain itself and would interact with one of the lowest layers of the atmosphere. And since that picture is taken in Switzerland, we have to assume that there are many water wells on that hill. Because I think that's northern Switzerland, which is limestone area, partially even almost karstic in nature. But there is a lot of water because I grew up there, I know. So water might be a very crucial ingredient in this whole process, what we are looking at here. Because yes, the clouds are made of water, but there is water also in the ground. And they're not separated, basically. And sometimes you see stuff like this up in the heavens. And you might even recognize here in this picture that it is maybe a twisting filament after all. Yeah, and it spans basically the whole sky as far as you can see. But it just didn't fit into the picture. And for example, when we talk about Birken currents, for those who know something about them, they probably think about this version of the Birken current. This basically very simplified version of the Birken current. And I think the one picture here on the left is in a way the picture of how a Birken current actually may look as it enters a planet. So it might be not so straightforward, so to say. And if we think about the Birkeland current probably being mixed up like this, then we have to assume that also all the other currents and current flows and stuff like that, they might have similar shapes every now and then. So a twisting filament might twist around itself many times, like we can see here on the picture, because basically that's all twisting around each other. That's very alive. It's moving all the time. I've been talking about volcanic plasma to some degree. This one is captured from the La Palma volcano, the dust devil. That's a plasmoid from the Agung volcano, just turned 90 degrees. And here we have, yeah, it's not really visible. But I think it's the Markland convection. Yeah, something like that. And here it's not that well visible, but we have hydrogen, helium, and oxygen here on the outer periphery of the Birkeland current, the electromagnetic separation of the elements. The lighter elements are on the outer side and the heavier are on the inside. We have the torus, stem tenon. If you don't know about stem tenon, go listen. It's worth it. Talking about the Earth's core and stuff like that, which I came to the conclusion it might be a plasmoid at the center of Earth. It's generating the heat. It's keeping the atmospheres of Earth in place, as it does, as we can see in the Sapphire project with the different shells, or the layers, the different double layers. And the amount of the layers, it's changing according to the amount of energy flowing through the whole circuitry. So maybe we have a similar thing on Earth. If the Birkeland current that feeds Earth has fluctuations, it might change the amount of the layers of Earth's atmosphere to some degree. I don't know exactly how many layers we have officially. Let's say we have 6 or 7. It depends where you look. And if there's a strong fluctuation, we might maybe just have 3 for a while. And that might be a very big problem, because if it does so, the weather will be very different. You know? There will be huge influence. If one layer just dissipates in one region for a while, we get very bad weather. Just think of a low pressure system. It gets down, the pressure gets down in a low pressure system. So there is an actual basically sink in our atmosphere. And for everybody who does plasma experiments, they use usually vacuum chambers in order to create the plasma. In other words, if the pressure lowers, let's say in a low pressure system, it is basically like if you would lower the pressure in a vacuum chamber. And the lower the pressure is, the easier it is for the plasma to form. Ta-da! That's why we get so much clouds when we have a low pressure system. But if I remember, we will touch this once again, the same topic. If I remember, maybe not. But that's just what I think. And again, that's a comparison from the La Palma volcano dust devil, captured from a live stream. And you will find these pictures in my volcanic plasma playlist. And the one on the left is a plasmoid I captured also from a live stream from the Agung volcano. And that's also rather maybe 3 years old or something. A very impressive tornado dust devil structure in Turkey some time ago. And then we have, of course, the plasma phenomena I have been talking about. That's the eruptive part of the volcano, obviously, and the one here on the right is the plasma phenomena associated to it. There is just a small little dot at the beginning, and then it just lights up. And first, it discharges downwards, and after the downward discharge is done, usually, I don't know if it's in this capture as well, then we have streamers that emerge upwards. No, we cannot see it in this one. Yeah, there's just basic lightning. Nothing to see here. We have a lenticular cloud. There we don't see the streamers here on this, but they are there. They don't reach up in this picture or this screenshot. But anyway, some time ago, Ben Hyde made an experiment in his garage or wherever he does his experiments. And as they were playing around with the pressure or the vacuum within this chamber, they seemed or they created a plasma that has or had these structures, which might actually be a spiral. It might be actually moving, we just cannot see it. But this, I think, like I mentioned in the earlier videos, is probably associated to the pressure conditions within the chamber. And it turned out that many years ago, maybe 7, 6, I don't know, I took a picture of a cloud that looks exactly the same as the laboratory plasma. And if I'm very lucky and I have the time, I have somewhere video footage of that, where you can see these things moving. I just didn't really have the time to search for that. So, I also showed this picture some time ago, and that's made some 3 years ago, when I have been talking about, I think, mountain water or something. But it's the same thing. Studying geology is studying petrified weather. And I just made this collage in order to show you that there are many similarities. And there are, like, undoubtedly. It's not a perfect match, but there are similarities. And later on, some time ago, I figured out to try to make an overlay of these two pictures. And after thinking about it, about something being the mirror image of something, I just turned around one of the pictures, basically the mirror image, and look at it. Now, I'm not saying that this cloud created these mountains, obviously not. But there are striking similarities between those two pictures. The cloud picture is taken in Finland and those mountains are in Romania, I think. But it's just somehow very nice to notice how repetitive even these kinds of more or less uh, complicated patterns can repeat. It's amazing. And as I try to somehow show how I think Earth's atmosphere is generated, or like can be active and is active and stuff like this, I just made a quick and simple overlay from the Sapphire project and Earth's atmospheric layers. And this is the thing I tried to explain earlier. Now you can see it. And it's in a way the same thing. Here at the center we have plasma, here at the center we have the plasma, and we get the layers. Same thing. So in order to have layers in our atmosphere, we almost need to think that we need, therefore, also plasma at the center. Otherwise there wouldn't be any layering going on. Okay? Earth's magnetosphere is a byproduct of the energy confined within the plasmoid at the center of Earth. In other words, when the energy input suddenly decreases, the magnetosphere will shrink in size, and therefore all the other layers of Earth's atmospheric layers would get thinner too. It might be even so that the numerical amount of these layers shrink, let's say from 5 to only 3. Such a massive change in Earth's atmosphere would quite likely lead to very bad weather. Okay, you get the idea. And I wrote this in 2023. And in 2024, there has been a paper, Long-Time Oscillations and Trends of the Mesosphere derived from 60 years of standard phase height measurements over Europe. An update. And here they say the mesosphere shrinking, subsidence, so they are changing, not only in thickness but also in height, as I tried to explain here, and as I tried to explain earlier with the Birkeland current that goes through Earth, keeping our plasmoid alive. So I tried to write about clay, and it's a hydrous aluminium silicate, if I remember correctly, all those complicated words. And then I started to once again make research about water. Hydrous, hydro, you know, the Greeks, snake, the serpent, the dragon. So it didn't take long for me to stumble around in the rabbit hole once again. And I remembered that not too long time ago, there has been this news about it doesn't need heat for water to evaporate, it just needs light. So then I was thinking about this, how does all this tie into telluric currents, geomagnetic activity, geomagnetically induced currents, the plasmoid at the center of the Earth, weather, the clouds that are plasma and stuff like that. And I found myself getting interested into Plasmon resonance. And let me share with you a quick part of one of the videos I have been watching about Plasmon resonance. And I really got tangled up in that theme, in that topic. Yeah, that's why one of the reasons I didn't manage to write more than a few sentences about the clay paper, because, yes, I started to make research about one thing and I found tens and dozens of others. I will, of course, put a link below to this video. Now let's just have a listen about what he's explaining, nano-manufacturing surface Plasmon resonance.
And to close the topic, I just have a few other short comments. One is we really didn't talk about how the surface potential is measured, or talk about another thing, which is the fact that in a real case, I said you can't pack all the counter ions up against the surface, but you do get some packing of ions against the surface. And therefore, you actually have a layer of counter ions that kind of sticks there, and then you start getting into the real double layer potential decay that we talked about. And this layer is called what's called the stern layer, or the stern plane, and then you have the diffuse layer where the potential decays smoothly as we derived. So in practice, what is typically called the surface potential is something that can be measured by doing experiments, for example, changing the pH of a solution and looking at the electrostatics of the solution, and that sometimes is what's called the Zeta potential, and you can actually use this potential in the equation for the double layer to calculate how the potential decays. It's because these ions stick to the surface, it's actually really difficult to know what the real surface potential is. But in practice, if you think about things like slip and flow, if these ions are effectively stuck at the surface, the real interfacial action is actually not happening right at the surface, but at the edge of this layer where you may have some ions stuck against it. So in reality,
Okay. He's talking about nano manufacturing. They are talking about very, very small things, ions, you know. They are so small you cannot see them with your bare eyes. But I thought, whoa, that's amazing. I have been searching for that thing for a very long time because what he doesn't know probably is that he probably provided one of the best clues of meteorology by now about certain cloud patterns. Let me show you what I mean. Let's just watch a few cloud pictures I took, I don't know, yesterday maybe, 2 days ago. Very recently. And I was very intrigued by seeing something like this after a long time. Because it doesn't happen often. There is obviously something going on here. But you can see in a way that the lower part of the clouds is rather defined. And here I increased the contrast a little bit more in order to emphasize a little bit more and bring forth some of the structures. Yeah, and there's a crater in the clouds. Man, I think there's a crater down below too, beneath the waters. And I don't think that's a coincidence at all. There might be something going on here, between the ground and the heavens. Yeah, and I think it was raining at one point when I have been there before I captured this picture. Yeah, it was the rain. Yeah, actually now I remember it was that day. I didn't really think about what picture I show you because I have many, many, many of those cloud pictures where you can see the lower surface very good. And it isn't always like that. For example, here you can see the lower boundary is rather defined. And you can also see how there is energy going up and does things. And also we can see clouds appear and disappear. Out of nothing into nothing. Wait a second, I maybe just noticed something. It may be... I have to put this here. There seems to be also a hole appearing. It might just look like that. Can you see it? Maybe it looks in a way the same like as we just saw from Switzerland. And I really just noticed this now. Yeah, on the right side we can see how there are clouds moving up. And on the left side we can see a fly. But in the middle, there seems to be something going on. Yeah, anyway, about the lower side of the clouds being sometimes rather defined and sometimes not. And it's in a way the same thing as we can see the lower part of the auroras. They just in a way stop somewhere and it's rather defined. There's like this double layer that defines the different layers. So now just to recap, in order for you to remember that where we were is the point, the most interesting thing. What I figured is the Zeta potential. Because it seems to be somewhere here, and it's the stern surface of shear. It's a little bit hard still for me to wrap my head 100% around this. But the Zeta potential. Because it seems to be that it's the thing that makes the actual double layer, the stern layer, I don't know, because here we have the Zeta potential, but here on this picture we don't have it. And it might be this one that creates this definitive distinction between the layers. So I made an overlay. That's the picture we just saw from the video. Yeah, it's turned approximately 90 degrees. And there's also Earth's atmosphere. And again, that's very oversimplified. But if we zoom in here and stop here at the exact right moment, we can see the surface of the Earth and the ions. And then we have the other ions and electrons, and there's another layer, the stern layer, diffuse layer, and all these kinds of things. And the Zeta potential, and he was just talking about it's being different, it will react differently. If you change just the pH of the thing, okay? If we are in a limestone environment, the water is rather alkaline because it contains much calcium and stuff. And if we go to the ocean, it contains much salt. And if it contains a lot of iron, it will again react differently. So there we have the changing ingredients for why and how certain clouds form in certain places or not. And if we are talking about the scalability of theories and stuff like that, it doesn't matter if we take something from the nanoscale and apply it to meteorology. Obviously, this diffuse layer and like the picture you can see here, that's nano. It's very small. And here we have half of the Earth, which is rather big. Principle is the same because we have a layer. And there are many layers, many surfaces, different kinds of surfaces on Earth. And they will all react differently according to their own electromagnetic properties. But I think the Zeta potential of our atmosphere is one of the key ingredients or key factors we need to understand much better in order to understand our weather. And if people would realize that clouds are plasma, it would help so much. And now I want to give a special thanks to Tom out of Germany because he sent me a paper a few days ago that was very interesting, and I wanted to share with you a few parts of that paper, and I really recommend everyone to read it and look at the pictures because there is so much amazing stuff. And my claim that clouds are plasma They haven't got any better confirmation than the stuff that is written in that paper. So now let's have a look at the paper Tom out of Germany sent to me. Thank you, Tom. That was an amazing paper you found. Scientific research. Open access. This year made extraterrestrial life in the thermosphere, plasmas, UAP, pre-life, fourth state of matter. Okay. Astrobiology Research Center, California, US. Department of Astronomy, University of Arizona. Biogeosciences Laboratory, University of Burgundy-Dijon, France. Department of Biology, University of Naples, Federico II, Naples, Italy. Department of Applied Physics, Palestine Polytechnic University, Hebron, Palestine. Department of Research and Innovation, Eco-Astronomy International Research Center, Tétouan, Morocco. Space Exploration Limited, Boyle Country, Ireland. Department of Zoology, Oklahoma State University, Emeritus, Stillwater. Yeah, mountain water. Department of Science and Medicine, University degli di Studi di Siena, Tuscany, Italy. Center of Astrophysics and Space Sciences, University of California, San Diego. Center of Astrophysics, Harvard Smithsonian, Cambridge, USA. So we probably have to think that this is a rather legit source of the text that is coming. Abstract plasmas up to 1 kilometer in size and behaving similarly to multicellular organisms have been filmed. Yeah, I have to concentrate on reading. Been filmed on 10 separate NASA Space Shuttle missions over 200 miles above Earth within the thermosphere. These self-illuminated plasmas are attracted to and may feed on electromagnetic radiation. They have different morphologies: cone, cloud, donut, spherical, cylindrical, and have been filmed flying towards and descending from the thermosphere into thunderstorms, congregating by the hundreds and interacting with satellites generating electromagnetic activity, approaching the space shuttles. Computerized analysis of flight path trajectories document these plasmas travel at different velocities from different directions and change their angle of trajectory, making 45, 90 degrees and 180 degrees shifts and follow each other. They've been filmed accelerating, slowing down, stopping, congregating, engaging in hunter-predatory behavior and intersecting plasmas, leaving a plasma dust trail in their wake. Similar lifelike behaviors have been demonstrated by plasmas created experimentally. Plasmas may have been photographed in the 1940s by World War II pilots identified as Foo Fighters. Yes, I will put a link below to this as well, but let me show you something. So now, chapter 14, Dusty Plasmas in Space. And one thing I want to mention is that this paper uses very easy language. I found it very easy to read this. They don't try to mask their knowledge or unknowledge behind very difficult words. They are just using the words you need to use in order to explain the stuff they're talking about. But on the other, that they are like talking very straightforward. I think that's very nice. But anyway, dusty plasmas in space. Plasma consists of ions, electrons, neutral gas, molecules, photons, and electric fields, a collection of elements that are exchanging mass, momentum, energy, electrons, and dust. Space is filled with dust, including the remnants of carbonaceous chondrites, with sizes ranging from macromolecules to pebbles. Because plasmas incorporate dust, plasmas in the thermosphere should be considered as dusty plasmas. When dust is exposed to UV radiation and immersed in plasma, there will be collective and individualized effects on plasma mass, charge, speed of movement, and behavioral dynamics, and the dust plasma will exhibit a variety of shapes. Dust plasmas can appear as spirals, rotating cylinders, bulbous with double voids, and in the shape of clouds that may descend into the lower atmosphere. For example, in the mesosphere, layer of the atmosphere below the thermosphere, those interacting dust plasma dynamics can produce noctilucent clouds, which can sometimes be viewed at sunset. It is also likely that plasma clouds that are embedded in lower atmosphere storm clouds or which drift alongside might be indistinguishable with the naked eye. So if noctilucent clouds are plasma, then we have to assume that all the other clouds are plasma too. If we think laterally. Because you cannot say, yeah, this cloud is plasma, but the cloud on the other side is not plasma, really. You either have plasma or you don't. And as I have been showing also in the beginning of this video, the comparison between lab plasma made by Ben Hyde and the cloud I once took a picture of and all these other things, I think that's all very well proved that cloud is plasma. And also when we once understand the Zeta potential, the surface potential, that's why we have sometimes the clouds that are very distinguish the lower boundary, or mammatus clouds, that's the same thing. It's about the Zeta potential, and the Zeta potential of the surface of Earth might be very strongly influenced by solar activity, geomagnetically induced currents, and stuff like that. And if there would be some shift in meteorology and they would consider being wrong, that there's no point in making any research in chaos theory or whatsoever. Instead, we just look out of the window and look at the clouds and start to understand. We could be much better off. Of course, it might require some new technical innovations in order to measure certain things in our environment better. Things as telluric currents or surface charge conditions and stuff like that. But for this kind of things, we probably need a bunch of nerds and these kind of things. Yeah, but I'm very thankful that I got provided with this kind of amazing paper. Just now, let's go on. I don't make any reading anymore. Let's just have a look at the pictures, because there is a huge amount of picture in this paper. Some might be familiar, as this one. The UAP everybody knows about, alright? Now let's just make a quick comparison. Try to remember approximately the shape of this. Okay? So here we have this UAP, and here we have the Agung Vulcano plasmoid, and also the La Palma. They have in a way a similar shape. As this UFO, or as they try to tell us, it's a UFO, but it's not. Yeah, maybe I have to write one of those people and tell them about volcanic plasma phenomena. Let's see what they think. Let's just look at some picture more than we are already at the end. Let me show you just a few pictures still, because they are amazing. They are tracking plasmoid movement. And the plasma tail they leave and stuff like that. That's amazing. Thank you, Tom, once again. So now we just have to figure out the Zeta potential of Earth, how it reacts to the environment, and how all that relates to geo-electromagnetic vortex directions that create high and low pressure systems and stuff like that. But anyway, clouds are plasma, and I think we have now very, very good proof of that. Yes. And if they just would understand still that water is a crystal and not a liquid, we would get even a step further. But anyway, that's maybe another theme of another day. But anyway, thank you. Bye.